We had started discussion on min cost flow problem. Let me just state it for you again. Yes, this was minimizing. So, given a directed graph, that's understood. This is over a directed graph GVA. Okay, let's minimize Z equal to summation Cij Xij Ij belonging to A subject to summation Xij summation over J minus summation Xki summation over K is equal to Bi, and we said 0 less than or equal to Xij less than or equal to Uij. These are and for balance this thing you had that I varying from 1 to n in this case is 0. So, this is a balanced situation where the supplies and the demands are all add up to 0. So, whatever is available is also demanded. So, the total thing fine, and we said that this is a necessary condition for the problem to have a feasible solution, and we will show that this is also a sufficient condition a little later on. I will discuss the special cases. So, then I started discussing with you a special case of this problem. I had given you some definitions. So, a special case. Special case, and this special case comes because your graph G is a bipartite graph. Okay, a bipartite means that you can divide the graph into two node sets where the connections are from one node set to the other. In other words, you can write your V as union of V1 union V2, right, and Ij belonging to A implies I belongs to V1 and J belongs to V2. So, you have only arcs going from nodes in V1 to nodes in V2. If you have this special case, then just see, look at the constraints, and I told you that we will take the supplies as okay, you can okay, leave them as BIs, but if the node I, and this is of course for all I, this constraint, right. So, consider a node in V1. So, that's we will treat that as a supply point, because arcs are going from V1 to V2. So, supplies are available here and demands are here. So, the nodes arcs go from V1 to V2 and you supply the amounts that are required at nodes in V2, right. So, for if node I belongs to V1, then you see these arcs are absent, and so this constraints will reduce to summation Xij summation over J varying from 1 to n, let us say, or okay, yes, and here, and this is equal to Bi, where we are assuming that I varies from 1 to n 1 to m, right. And then similarly, when it is a supply point, it is a demand point, that means a node is in V2. If a node is in V2, then there are no arcs going out of V2, right. The arcs are only going from V1 to V2. So, this part will be 0, and therefore, this will reduce to minus summation Xki summation over K. This is equal to Bi. In this case, or maybe I should, okay, let me write this as J, just to make distinguish between. So, J varies from 1 to n. So, that means I am assuming that the cardinality of this is m and cardinality of this is n, and so the cardinality of V1 U2 V2 is m plus n. So, the total number of nodes is m plus n, and you have this. So, here this is fine, because your Bj's will be negative. The demand quantities are negative, we treat them as negative, and or if you want to be more specific, just write Bj here, right. So, we are assuming that Bj's are less than 0. So, this becomes minus Bj, sorry, I mean Bj's are all greater than 0. So, minus Bj is negative. So, this is so this special. So, these constraints will reduce to this special structure. Okay. You can take a small picture, just take a situation where you have 1, 2, and then you have 1, 2, and 3. So, this is your V1, this is your V2, right. So, we are saying that the arcs are going from here to here, yes, and this is this and this. Okay, I'm right now assuming that you have arcs going from 1 to all the markets. Similarly, from 2 also you have arcs going to all the markets, and we will later on consider the more general situation when every supply point is not necessarily connected to every demand point. Fine. So, this would be your transportation problem, and here your decision variables. So, for example, x11, x12, x13, these are the decision variables connected to your first supply point, and x21, x22, x23 would be the decision variables related to second supply point, and you have to decide how much to send from where to where, given that you have a this is B1, B2, and this will be B1, B2, B3. So, the confusion will not arise because the when you formulate the problem, it will be clear which is supply and which is demand, though some of the textbooks also write these as the supply points, the supply amounts, and D1. So, the names are suggested. These are the M supply quantities and these are the N demand quantities. So, you can also formulate the problem with SIs and DJs, that is okay. Yeah. So, let us see now the simplifications just come through, and because we are looking at the structure, special structure. So, here also we said that because of, so this condition holds, right, because that is a necessary condition. Even when we take the special case, the necessary condition holds, and in this case I will show you for the transportation problem right now, and then in general that this is also a sufficient condition for a feasible solution, for the problem to have a feasible solution. So, at least for network flow problems, feasibility is not a big concern, right, and once you put this condition, then you are sure that there will be a feasible solution always. So, we do not have to worry about phase 1 working out with phase 1 and so on. Okay. Now, let me just also show you that so the node arc incidence matrix in this case, what will it be? So, the constraint node arc incidence matrix is actually m plus n by m plus n, sorry, mn, because your number of variables are mn, right, m supply points, n demand points. So, if you have connections from every supply point to every demand point, this will be mn. So, mn arcs and m plus n nodes. So, the node arc incidence matrix will be this, but how can you, and you see that if you look at the column aij, that means the column for the arc connecting node I in the supply point to node j in the demand set, and aij will actually look like ei and ej, where ei is m dimensional unit vector, right, and you know that this indicates that it is a unit vector with 1 in the ith place, all others are zeros, and similarly Ej is n dimensional unit vector. Okay, this is unit vector. Okay, so you have m plus n elements here, because m plus n rows and mn columns to this thing. So, you have this is a very simple structure, and you will see how your calculation of the simplex quantities becomes so simple. Okay, now, just one more thing here. See, if you add up as we did for the flow problem general, if I add up these constraints, so this will be with respect to I, and I sum up these with respect to j. So, you see these quantities will be the same, because here you are summing up all the xij's, here also you are summing up all the xij's, and so sigma bi. So, what will it be? So, when you add up these things, yeah. So, now I sum up this, I add up these with respect to I add up these with respect to j, add, then you get 0 on the left hand side and also 0 on the right hand side. So, what does it show you? That the so this tells you that the rows of A are linearly dependent, right? Because since the sum of the rows is the 0 row. 0 row. It's understood. You know what I mean. Okay, all components, right? So therefore, this implies that rank A is less than or equal to m plus n minus 1. Fine, because it has m plus n rows, and I've shown you that all the rows add up to the 0 row. So therefore, the rank has to be at most m plus n minus 1. Okay. Now, what I'll show you is that the claim is rank A is actually m plus n minus 1. Okay. So, take the general situation here, and as I showed you that these are the columns. So, what I am suggesting here is, okay, if you want to first look at an example. So, for example, for this matrix, for this problem 2 by 3, where 2 supply points and 3 demand points, what would be your so first of all, so for the 2 plus 3 5, for the 5 by 6 node arc incidence matrix, so I am taking a particular example and then show you that the proof for the general case matrix. For the matrix, okay, maybe not for, I want to say that the 5 by 6 node arc incidence matrix will look like as follows. Okay. So, we said that the first one will be E1 E1. So, that will be 1 0, this is 2 dimensional, then 1 0 0, that is the first corresponding to x11. Then this will be again E1 and E2. So, this will be 1 0 0 1 0, then E1 3, like E1 and E3. So, you are numbering the columns as x11, x12, x13. Then you will have x21, x22 and x23. So, these are your columns, the corresponding arcs, and these are the nodes 1 2, and these are the 1 2 3 for the supply, right. So, it is something like this. Fine. So, x13 would be 1 0 and this is 0 0 1. Fine. Similarly, for 2 1 will be 0 1, then 1 0 0, because it will be E2 and E1. Similarly, this will be E2 E2. So, 0 1 0 1 0. Then E2 3 would be 0 1 0 0 1. So, this is what your matrix will look like. Then node arc incidence matrix, and we are saying that, and so what we were saying here is, okay, by the way, I should have written minus sign. Okay, later on we'll revert to yeah, okay. So, right now I am writing the constraint with the minus sign, but since you see both sides it's negative sign, so we can do away with the minus sign. But right now the showing you the rank is actually m plus n minus 1, it will be easier. So, let us keep the minus signs and then later on we will remove them. So, here you see what we were saying is that if you add up these 2 rows, you get 1 1 1 here, right, and if you add up the last 3 rows, you again get minus 1 in all the 6 places, and therefore, the sum of these 2 rows is minus times the sum of the last 3 rows, and so they add up to 0. So, therefore, the rows cannot be linearly independent. So, the rank has to be less than or equal to m plus n minus 1, is what we are saying, right. And now, to prove that the rank is actually m plus n minus 1, I will demonstrate to you a basis. If I can show you that there are always m plus n minus 1 columns present in the node arc incidence matrix which are linearly independent, I am done, right. So, we can also have a proof which is which uses method of contradiction, or it uses the method of construction. So, that is what we are doing. We are going to construct for you a basis. So, let us show you the proof is simple. So, now you have this picture in mind as to how the node arc incidence matrix looks. So, claim is this, and I am saying that for the general matrix proof, consider the set of columns, set of m plus n minus 1 columns as follows. I am saying consider A11 to A1n. So, the first n columns, right, A11 to A1n. Then I want you to choose, select a column which would be, this will be A21. So, you see, actually you saw that here in this case corresponding to each supply point you have a block of rows, columns. So, like x11, x12, x13, then here you had x21, x22, x23. Similarly, if you had another supply point, it will be 31, 32, 33. So, for each supply point you have a block of columns. Okay. So, this will be so then from the first block I am selecting all the n columns, then from the remaining m minus 1 columns I will select one column, first column of each. So, A21, A31 and finally AM1. Is it okay? Yes, A21, A31, AM1. Okay. So, how many you have? M minus 1 here and n here. So, the total number of columns is m plus n minus 1. Okay. So, therefore, what does it look like? See, I can write it out, E1, E1 and so on, E1, En. These are this. Then this would be E2, E1, E3, E1 and so on, Em, E1. These are the, and by the way, what you should do is sit down and find at least more than 2 different sets of such columns which are linearly independent. I have chosen one for you, and so you see now here there is a 1 here, right, but the ones in the remaining part is at different places. Okay. So, for example, if you choose the column E2, so E2 has a 1 in the second place, but there all these, see, your breakup is like this. So, these are the supply constraint rows corresponding to the supply points, and these are the rows corresponding to the demand points. So, here E2 second place, there is no 1 here, and similarly there is no 1 here. And so, this column cannot be expressed as a combination of linear combination of these columns, because all other columns in the matrix have 0 in the second place. Similarly, here E3, all columns, all the remaining columns have a 0 in the third place, and so on. Yeah. Okay. And so, none of these, and similarly here none of these columns can also be expressed because they have 1 in the first place. None of these columns have a 1 in the first place. And here you see for these columns you may say that there are 1s in the first place, but then here this is the identity matrix, because this is 1 in the first place, and second 1 in the second place, and so on, and this will be 1 in the nth place. So, this set is right. Consider a set of this, therefore, can easily argue. So, I am not writing the argument here, can easily argue that this set is linearly independent, that this set is linearly okay, write it legibly, is linearly independent. So, therefore, I have shown you that the rank. So, please sit down, and while you are going through this material, you should be able to write down many more sets of columns, m plus n minus 1 columns, which are linearly independent. Okay. So, the rank is m plus n minus 1, and so what we can do is, So therefore now I can get rid of the minus signs, and my so I'll start with the transportation problem and write down the, so we can now start looking at the how the simplex algorithm can be simplified, and we can we need to define a few more because I have to translate the concepts of these simplex algorithm to the transportation problem. So now this is our transportation problem, and if you want to distinguish, I mean people, so this is balanced one, balanced transportation problem, because you can have a situation where the sigma bi's are not 0, or if I remove the plus minus sign, then the sigma bi's with respect to the supplies, the total supplies are equal to the total demand. We say it is a balanced transportation problem. So we are writing this as minimize z equal to summation Cij Xij, and so okay, you need to write, so I belongs to V1 and j belongs to V2, subject to summation Xij, j varying from 1 to n is okay. So let's write Si, I belonging to V1, and summation Xij, summation over I varying from 1 to m is Dj, j belongs to V2, or 1 to n, fine. And we are not putting any Xij greater than or equal to 0, right, for all ij. That means the upper bound constraints I am right now ignoring. I am saying there are no upper bound constraints later on. So this is really a special case of the general min cost flow problem that I formulated for you, and then we will come back to the upper bound constraints also, the upper bounded version of the transportation problem. We will visit that after some time, but right now I want to develop the simplex algorithm for this and show you the simplifications, and then one can always bring in some more complications. Okay. So this is our transportation problem, and we have said that the rank of the coefficient matrix A is m plus n minus 1. Yeah. Let me show you now that this basis matrix for the transportation problem has a special structure. Okay. So let me define this for you first, a triangular matrix. A triangular matrix. So what do we mean by a triangular matrix? Okay, that's a definition. So triangular matrix. So matrix B, a matrix B is said to be triangular if it can be written as a lower triangular matrix it's not necessary, but doesn't, I mean, you can see if it's a lower triangular, then you can again transpose it and get it. If it's an upper triangular, then you can transpose it and make it lower triangular. So this is no there's no restriction. Okay, it can be written as a lower triangular matrix by permuting its rows and columns. Its rows and columns. Okay. So this is what a matrix is said to be triangular. So if it can be written as a lower triangular matrix by permuting its rows and columns. Okay. And so what would that mean? That here, so it has the following properties. A triangular matrix satisfies, the matrix satisfies the following properties. Okay, what are the properties? One, there is at least one row with a single entry, with a single non-zero entry. See, when you say lower triangular, it means essentially, you see, so this is 0 and you can have entries here, right? Okay. So that means, you see, for example, here the first row will have only one entry, all others are zeros, right? So there is at least one row with a single non-zero entry. Okay, I'll explain, because again this may sound like a restriction. Okay, there is at least one row with a single non-zero entry, fine, and then after deleting the row, this row and the column with the non-zero entry, the reduced matrix, which will be m plus n minus 1, m plus n minus 2 by m plus n minus 2, also has the same property, which has property 1. Okay, that means again you can find a row with one single non-zero entry. Okay, here by the way, we are defining this for a basis matrix, because I am saying non-zero. See, okay, let me write it down. A zero matrix is also lower triangular, by the way. Yes, because all entries are 0, so it's lower triangular. So we are actually here defining a basis matrix, because I am saying non-zero entry, and it should be clear to you why. So maybe somewhere I should say that a triangular matrix, a triangular non-singular matrix okay, this is important, a non-singular. And triangular, so it's understood it has to be square matrix. A triangular non-singular matrix satisfies the following properties. So since it is non-singular, the determinant cannot be 0, right? And for a triangular matrix, you know, for a triangular matrix, what is the determinant? So this determinant is the product of the diagonal entries. So the diagonal entries, if any of the diagonal entries is 0, the product is 0, and so the determinant is 0. So therefore, since it is non-singular and it is triangular, therefore there is at least one row with a singular with the single non-zero entry. Okay, and that becomes the we will make it the diagonal element, because we will bring that row to the top, right? Then what we are saying is that you remove this row and the corresponding column, then what you are left with is again a non-singular matrix, and since it is triangular, it will again have a row with single entry, right? Because this second row now will have a only one non-zero entry, right? Because this one has been struck off. So therefore, you can again bring that row into the second position and continue with it, right? So this column with a non-zero entry. So after deleting this row and the column with the non-zero entry, the remaining m plus n minus 2 by, or okay, why am I bringing this here? The remaining matrix, remaining submatrix has property 1. So once, so therefore, a triangular matrix can always be will always satisfy these two properties, and therefore we can always keep bringing the rows, consecutive rows here in the top, and then we will come to a triangular matrix, right? Okay. So so therefore now we say that the basis matrix for the transportation problem So, we remember we want a square matrix. So, here as it is, I am taking the columns, it say if you take the m plus n minus 1 columns, and they will be m plus n by this thing. So, I will remove the, yeah. So, we will say that the basis matrix for the transportation problem with the last row removed is m plus n minus 1 by m plus n minus 1 triangular matrix. Okay. So, when you remove the last row, you have only m plus n minus 1 rows. So, therefore, the matrix, the basis matrix becomes m plus n minus 1 by m plus n minus 1. It is non-singular because it is a basis matrix, and we can show that it is a triangular matrix. Okay. So, if you want, you can write this as a theorem or whatever it is. Okay. So, you need the proof. Yes. Now, this is the time we are going to exploit the special structure, because denote let B be a basis matrix and if it has twice m plus n minus 1 positive entries. So, yeah. So, now I am referring to this situation, right. I have taken remove the minus sign. So, 2 m plus n ones, or write just ones, right. Then it is not non-singular. Yes. Why? Because B is a basis matrix. So, if it has twice m plus n minus 1 ones, then that means what? That means that every column has 2 entries, because there are only m plus n minus 1 columns, and if the total, and each column has only 2 entries. So, if it has twice m plus n minus 1 ones, then every column must be having 2 entries, and we saw that you can add up the supply rows and the demand rows and the sum, and show that the linear independence is not there, right. Okay. So, then it is not non-singular, right. Therefore, it has only m plus n minus 1, what shall I say. So, therefore, it has, you can simply say that it has at least, or why should I say at least, I should say that it has a column with exactly single 1, right. So, there must be a column, since it cannot have twice m plus n minus 1 ones in it. There must be a column which has only a single entry, which is a single 1, right. So, it has a column with exactly single 1. Place this column in the m plus n minus 1th position, right. I bring it to the last. Yeah, I should have pointed out here that in this definition we use the word row, but as I remember, since we are saying that permutations of rows and columns are allowed, so even if the same applies to a column also. So, please, I should have pointed this out, that the definition I simply wrote the word row, but it also can be for a column. So, if column wise also the matrix has the same property, satisfies these two, then also it is triangular, because then you can if you can write it as the upper triangular, you can again transpose and take the, right. So, there is no problem. Place this column in the, so therefore, the column with the single entry I will place in the last position. See here, see this column, the last column has single entry, right. Then you remove this row, and that means now place this column in the this thing. Now remove this column and the corresponding means the row having that positive single one, this column, and corresponding row from B, and the remaining the submatrix again, because we are using the property that if a matrix is non-singular, then every there cannot be any square submatrix of the of a basis matrix whose determinant is 0, right. So therefore remove this column and corresponding row from B, the reduced matrix has the same property. That means it is triangular. What do we mean by that? Has the same property that you can again find, because the reduced matrix again will not have, that means see, when you have removed a row and a column, the reduced matrix will be of size m plus n minus 2. So it cannot again have twice m plus n minus 2 once in it, and so you will be able to find another column with only one single non-zero entry, which is the which is 1, and then you can place it the last second, and so on. So therefore you continue with this, right? Continue with this, continue to obtain a triangular okay. So we just discussed that a basis, any basis for this will be a triangular matrix, and what was the property we basically used? We said that at every, while trying to write it, while trying to transpose permute the columns, we can always make sure that because it is a non-singular matrix, there will be at least one column with a single entry, non-zero entry, and so I can place it as the last column. Then when I remove this column and the corresponding row, I will again be left with a submatrix which is non-singular, and therefore it must have one column which has only a single non-zero entry. So I will place it here, and so on. See, so basically I am exploiting the idea that for any non-singular matrix here, for this particular coefficient matrix, will have will not have all columns having two ones in it. Essentially we are using that property, right. And as I go on deleting a column with a single entry and the corresponding row, I will again be left with the submatrix which has a column which has only one positive entry in it, which is a single one. So essentially we are using this, and we will reformulate this in another way. So in any case, when you have this, see, what is the idea behind trying to show that the basis matrix is triangular? See, if you have for any triangular matrix, for any triangular matrix, say A, okay, what do you want to call it here? Let us say C, matrix C, right. The system of equations Cx equal to, let us say, D can be solved very easily by the method of backward substitution, of substitution. Okay, how? Because see, the first equation will look like, see, this is C11 0, then this is C21, C22 and 0, and I am assuming that matrix C can be solved where, well, I am assuming that determinant C is not 0. So it is a triangular matrix, the determinant is not 0, that means all diagonal entries must be positive, must be non-zero. Fine, this is how you have it, right. Then this will be, let us say, CM1 and so on, it will be CMM. So this times x1 xm, suppose you have this system is equal to d1 to dm. So, this is your system here, right. Now, you see, because this is a single entry here, this equation reduces to, so the first equation reduces to, first equation is C11 x1 is equal to D1, which implies that x1 is D1 by C11, since C11 is not 0. Well, all diagonal entries are non-zero, right. So, once you have the value of x1, the second equation is, and the second equation is C21 x1 plus C22 x2 is equal to D2. Now, since I already have the value of x1, I have the value of x1, this implies that C21 into D1 upon C11 plus C22 x2 is D2. Yeah, I am just showing you the details so that you get the idea in your mind, get it fixed, and therefore, this implies that your x2 is equal to D2 minus C21 into D1 C11 into 1 upon C22, where again C22 is not 0, right. So, by this backward substitution, you can immediately get your solution to the system of equations, right. Now, for the triangular case, in the case of, okay, I should say, in the case of transportation problem, the CIIs are all ones, because every column has only 2 ones in it and it is a non-singular matrix. So, these have to be ones. Therefore, for example, in this case, what does it become? And so, see, the thing is that, to simplify notation, because since we have permuted the rows and columns, so something, whatever was S1 will be something else and so on. So, I am not going into it, but the basic, you can just translate this concept to the concept here, in the sense that if your matrix is triangular and you are solving this system of equations, then you can, this, the first equation will be what? So, the first equation would be something like C11 is 1. So, it will simply be, okay, I am calling x1 here, but it will be some particular xij. So, x1 will be simply D1, right. And then similarly, x2 would be what? From here, just put your C11s and C22 to 1s. So, this will be D2 minus, again C21 will be plus 1. So, this will be something like D1. Yes, because the entries in this matrix for the transportation matrix are all here going to be plus 1s and zeros. So, it is possible that this is either D1 or this may be D2, does not matter. But so, therefore, you can see immediately that because the triangular matrix, because the basis is a triangular matrix, the basic solution. So, a basic solution, a basic feasible solution for, let me refer to this problem as 1 here. So, a basic feasible solution for 1 will be of the form sigma, you can say alpha I S I varying from 1 to m plus sigma beta j d j varying from 1 to n, where alpha i's and beta j's are either 0, plus 1 or minus 1. That means, it will be some combination of adding, subtracting the si's and dj's. Yeah, if you just translate this, because my d1s are simply si's and dj's, right, and the coefficients are the diagonal entries are all 1s, and these can also be only 1s or zeros here, the entries, because every column has only 2 entries. So, obviously, the question of all these being positive doesn't arise. It's just that you'll have some ones here, then some ones here, but diagonal entries will all be ones, and so you'll be adding and subtracting the supplies and demands together. So this is this, right? And so you immediately have this property that in case SIs and DJs are all integers, then your basic feasible solution will also be integers. Yeah, or since it will be simply adding or subtracting integers, there is no division involved here. So therefore your basic feasible solution will also be. So therefore every basic feasible solution of 1 is integer valued if the SIs and DJs are all integers. Now this is a very nice and very good property of the transposition, and that this has been possible. We could show it because we could exploit the structure of the constraints, right? And the moment in a linear programming problem, the moment you impose the condition of integrality, that is, you want your variables to be integers, then the problem becomes very difficult, a general problem. But then we want to show you that there are cases of the linear programming problems which have this special structure, and therefore you can show using the structure that a basic feasible solution will be integer valued, and that really helps a lot, because in such situations when you have, if you are transporting barrels of oil and so on, then because these supplies will be in integers, the demands will also be in terms of number of barrels. You are sure that your linear programming solution will not give you, half a barrel or 1/4 of a barrel or something like that. The basic feasible solutions are all integer valued, so one of them will turn out to be optimal, and hence you would not have the embarrassment of having to make 1/10 of a barrel or something like that as an optimal solution. Okay, so this is that, and yes, so you can immediately show have this property from the triangularness of the basis, and you want me to take up an example here, or okay. So now what we want to show you is that how do I progress with the simplex algorithm. So I have showed you that a basic feasible solution will correspond to this triangular basis. So we will not actually work with the simplex tableau, but again there is a simplification here, and I will talk about the transportation array. So let me say this, how do I actually represent this. So this will be a transportation array, and again the idea is simple. See, what I will do is I will write it as a collection of these cells. So here this is, so m rows corresponding to each supply point, and then you have 1, 2 and so on, and these are your demand points. So for example here you have these mn cells. So you obviously you can immediately connect that a cell corresponds to a column here or to an arc here. Okay, we will have these mn cells here. Fine. So for example the ij cell, we will not really need to compute and update all these columns and so on. The nice way, I mean, of course you need the updating of the incoming column and so on in the basis, but it will all be, we will be able to show it through this. So now here we have to translate the concept of a basis here, because you have these mn cells. So for example your ij cell corresponds to arc ij, right. So therefore the corresponding column for the cell is your aij, column which is made up of EI and EJ. Okay. And so how will I translate the concept of independence of a set of m plus n minus 1 columns to this representation or this transportation array, right. So the idea is that, so we will say that a set of cells in the array is linearly independent if the corresponding set of columns is linearly independent. Okay. So the same thing, that means here the cells. So for example, you cannot have these 4 cells as linearly independent. Why? Because you see, if you write down what would this correspond to, say for example, so we are saying for example cells 1 1, 1 2, then 2 1 and 2 2 are not linearly independent. So we can argue, see for example, I will write 1 1 as E1 and E1, right. Then what I can do is 1 2. So I will write this as minus E1 E2, right. Then I will come here, I will say plus E2 E2 and then minus E2 E1. So just look at this. Alternatively, I have these 4 cells, and alternatively, because I am able to go from here to here, first row, and then you come here, second column, right. Then from here I move downwards along the column. So this becomes 2 2, and then from here I go to the first column. So this is 2 1, and then this. So therefore you have this here. You see, this one will cancel with this, because 1 in the first place, 1 in the first place. So this entry goes away. Then you have 1 in the second place, in the second set, and you have 1 in the so plus and minus 0. And here also this is minus E2 plus E2, and this is E2 minus E2. So this is 0 0. Now here these are vectors. This is m dimensional vector and this is n dimensional vector, right. So this set. So therefore the same concept. That means, and what is happening is that each of the columns here, you can see each of the columns has 2 1s. This has 2 1s, this has 2 1s, this has 2 1s, and this has 2 1s. Okay. So the columns are linearly dependent. So therefore the cells will be linearly independent if the corresponding columns are linearly independent. And yes, so how do I now obtain? So that means if I have, so suppose again, just to give you an example, if you have a set of basics, so that means linearly independent set of m plus n minus 1 cells will form a basis. Yeah, but whether it will lead to a basic feasible solution or not has to be seen. And here again, let me take up an example. So essentially what we are saying is that fine. So let me just tell you, a linearly independent cell, a set of cells will form a basis, but not but may not. So may not, but okay, but may not give you a basic feasible solution, right. Just as for the simplex algorithm, you have a basis, but that does not necessarily mean that you will it will lead you to a basic feasible solution. So the idea is that how do we make sure that we have a how do we obtain a basic feasible solution given a set of m plus n minus 1 basic cells, or how to obtain maybe given any basis, how do I go about obtaining a basic feasible solution. So that will be the, so in the next lecture we will concentrate on essentially building up the simplex algorithm for this special case, for this special structured problem, and you will see the simplifications that you can, and it's amazing that by exploiting the structure you can make life so much easier. Okay, so this is what we will attempt, how to obtain. That means the things that we have to now look at is, how do I get a starting feasible solution, basic feasible solution? Once I have it, then how, when I want to improve or go to a better basic feasible solution, there will be a simplification, and finally you can continue with the simplex algorithm for solving the problem. So that should be the next lecture.